Before you can race, we want to understand and implement basic algorithms that will prevent the race car from crashing into obstacles, walls, and other cars. So we're going to learn about AEB, or automatic emergency braking, and how to make your car crash proof. And this will lead us to our lab on building a safety car. As always, this course is a team effort with contributions from a variety of individuals. We are grateful for learning from each other. So today's lesson plan is split into 5 parts. First, we just understand automatic emergency braking on the road, how it is used by today's cars, and what is the roadmap for cars in the years to come. What are the hazards today's cars see and how do they respond to these? Then we'll look at a variety of range sensors for autonomous vehicles, and specifically those ones that are applicable for automatic emergency braking. And then we'll learn to work with the laser scan data for the laser that we use in the F1TENTH car. But now that's all the kind of mechanisms and the implementation. But when you want to put this together in software, you first have to have a clear concept on how do you measure safety, and what is the equations for safety? How do you capture the distance between your car and any kind of critical objects, and the rate of change of the distance between these objects, and how we combine those two together to capture ways to measure safety. And then we'll have a quick overview of the lab that is to come on building the safety car, where you will implement AEB on the F1TENTH car, both in simulation and in the real F1TENTH car. So let's look at AEB on the road in today's vehicles and how it's being used, right? So to implement AEB, we first need to observe the relative speed and distance between our car and the vehicle in front of us. And so here we're just looking in one dimension because the radar is in the front of the car, and it can capture when the car in front is slowing down and the rate at which it is slowing down. So it's really looking at when there is a crash imminent, it flashes a alert message. And if the driver does not respond in time, the car automatically starts braking. And if there is a sudden change in this combination of distance and the change of distance, the rate of change of distance with respect to the vehicle in front of us, then the AEB will hit the brakes even harder to prevent the crash from happening. So AEB has actually been shown to be very effective in crash prevention and in saving lives, to the extent that at the end of 2021, the European authorities have mandated AEB, or automatic emergency braking, to be a standard feature in the cars being manufactured in the future. And this will include a variety of related AEB technologies, such as forward collision warning, as we saw in the previous video, crash imminent braking. So this is not just giving you a signal to the driver in terms of an audio or a visual signal, but also taking over the controls from the driver to prevent the crash from happening. And this would include, parts of this would include like dynamic brake support, where it would pre-charge the braking system in anticipation that if the driver activates the drive-by-wire braking system, then it will be able to actuate much faster. And in addition, there is lane departure warnings, rollover resistance, and blind spot detection, which are all basically keeping a safety bubble in the near frame of the vehicle. So what you will do in this upcoming lab is implement AEB in the F1TENTH race car. And you'll prevent the car from crashing by trying out new algorithms. And you'll understand the nuances in real-life implementations of capturing the sensor data and different failure modes, and to the extent, or say the maximum speed up to which your AEB works, and anything faster than that is not able to respond fast enough or brake fast enough. And so you will implement what we call time to collision based braking, and we'll walk you through that. And essentially your car, if we put a static obstacle in front of it, it will automatically stop over here, whether it is being driven by a joystick or a keyboard, or it is driving autonomously. So before we get started on how you implement it, let's start with how would we generally start to think about AEB? What kind of vision processing pipeline do we need in order to get this kind of awareness? And so very much about like object detection, tracking, and prediction. And but what is the bare bones minimum information that we need to engineer an AEB system? What is necessary to fuse the radar, which gives us the distance, and the vision pipeline, which classifies objects? In the most basic implementation, we don't need to know what type of object it is. Is it a car, truck, or motorcycle? As long as it's a moving object, that's what we are interested in. And then the next thing we need to know is we need to find the pose and the velocity of all the vehicles in our vicinity. The third part is we need to then isolate of all these vehicles, which ones are critical to us. That means that they pose the highest risk in having a crash. For example, the nearest vehicle may not be the most critical if its relative distance is not decreasing rapidly. Finally, once we identify the most critical vehicles, then we need to check if there is imminent collision and what is the possibility of that. So this usually is done by forward simulation, and this is usually an offline method, or an online or in real time. You would have trajectory-based estimation algorithms that assume certain basic kinematic models of vehicles, and this can then forward predict what is the potential collisions or potential for collision, and determine what response it should have. So how should we go about building this critical, object detection and evasion system? I mean, we could have a camera to detect and classify objects, and also detect lanes to estimate their heading. We can track objects across multiple frames to estimate their velocity and their acceleration. And with the radar, we can estimate distance. Then fusing the camera and radar inputs, we can then analyze each vehicle's potential for crash. But perhaps there is a simpler way to get started. We need to know which objects are either critical or not critical. So we don't need to know what type they are really. So we basically just need a binary classifier, critical or non-critical. While this can be done with some machine learning based algorithms, at the core, we just need to determine an adaptive threshold for critical or non-critical objects. And so we are just going to use classic methods, physics-based methods, kinematics-based methods now. And then later on the semester, we will use some more machine learning-based methods. Our general philosophy in this course is first you learn the algorithms and you learn the problem and how to solve it. Then you can use machine learning and let the machine learn for it afterwards. So let's get started, right? So if we have this binary classifier, it gives us this kind of output over here. So these features such as automatic emergency braking, they are meant to improve the safety of vehicles by reducing both the frequency and the severity of accidents. Unfortunately, they usually usually have a long development cycle, and the effectiveness is difficult to quantify because there are many conditions in which they need to operate. So let's take a look at this output of our binary classifier. So in this 2x2 matrix, we see these possible success and failure outcomes, what the classifier outputs and what is reality. So on the y-axis, we have the classifier's output and says, okay, I think that there is a true critical case over here or not. But the reality, which is also known as ground truth, this could be measured after the fact or could be measured with alternate sensors just for evaluation purposes like a LIDAR added on. So what do you think these 4 cases mean? Can you think of an example for each? And which one is life critical? Let's take a look. So here are our 4 cases, right? So the true positive correctly detects the critical object and exerts the braking. I mean, it's meant to do that and it's doing exactly that. The true negative means that there was no critical object and the classifier did not detect any case, right? So nothing happened. It also says nothing happened and nothing was done exactly the way it should be. So that's all good, right? So now we have 2 false options. Which one of these do you think is a more serious problem? for AEB. So first, let's look at the false positive, right? An error in our binary classifier where it detects a critical object and breaks, but actually there was no critical object, right? So this is aligned with the engineering incentives to make the car safe. And it's better to be conservative and have a few false positives because we want to err on the side of being safe. And if there is a slight doubt whether the object is critical or not, and we hit the brakes, that's okay, right? So, however, this results in very unpredictable and a jerky ride experience if it happens too frequently, and the customer may not enjoy it, right? And therefore, the customer might turn the system off, and future customers may elect not to buy this kind of system. So then let's take a look at 3 examples where this AEB actually breaks, but there is no critical situation in front. In example 1 on the left, you can see you're driving on a street and maybe the car has detected something on the left or something on the right and decided to brake the car while it was driving. And then you're like, okay, well, that's bad. It's annoying at first. And you think something with the car is wrong, for example, but then you drive on, right? So, and then there's number 2 where there's actually nothing on the street at all. And the car, jerks a little bit. And even though the eminent, the car in front is quite far away. And then the example number 3 is where you see a lot of cars are driving in traffic now on the highway and AEB is applied. There's nothing in front of us, but well, it could have caused a crash with the vehicle in back because the vehicle behind was, may not have kept enough distance, but was not expecting us to have a sudden stop. So while it's not super serious for us, it's basically like a bad application or a bad implementation by the automotive safety engineers. So to answer the main question, which is the most serious problem out of these 4, it's the false negative case, which we should worry about the most. The test result incorrectly indicates there is no presence of a critical condition when there actually is one. So false negatives kill innocent people, and regulatory and insurance providers have incentives to look at the false negative rate. In fact, if we look at an example now by a driver in Uber, we can see that and here this is the Uber driver in Arizona, and this car basically hits a pedestrian, and so essentially what we see here, the AEB was assumed to be active by the safety driver, and the LiDAR first detected the pedestrian about 6 seconds away. That's about 378 feet or 115 meters before impact. And then during the next 4.7 seconds, the self-driving system did not infer that emergency braking was needed. And then the emergency braking only kicked in at 1.3 seconds before the crash, but it was too late. If the car was driving at 25 miles per hour, it may have been okay because it could have stopped at that speed. But the car was driving at 43 miles per hour, and then basically the pedestrian was killed. So an unknown object was detected by the system and was not able to classify this bicycle. Sometimes it's less important to know what the obstacle is, and we just need to know that there is an obstacle there, right? So poor fusion and camera of the systems can be blamed here, but that's missing the point. So ironically, the Uber drivers had actually turned off the AEB system because of the high rates of false positive incidences, which made the ride uncomfortable. And now you see that by turning off the system because of false positives, it actually resulted in this kind of accident here. So later on, the Volvo engineers actually, not the Uber engineers, the Volvo car engineers, they turned on the AEB to demonstrate that actually Volvo has implemented AEB correctly. Incidentally, at the end of the day, the safety driver was charged with negligent homicide in the death of the pedestrian struck by the autonomous Uber SUV. Uber was not blamed. So lesson 1 is, if you're in an autonomous vehicle, ask the main question: who is responsible in the case of an accident? If they say the human, then don't use that vehicle because they are not backing up their technology there. Lesson 2, which is now more practical for us over here, is that as an engineer, your goal is to have a high true positive rate and a high true negative rate and a low false positive rate and no false negative rate to as much extent as possible in the system that you're building, right? So no false negative rate is very crucial here. In fact, the automotive industry has now taken this as a mandate, and they are starting to figure out a system where they can allocate points or stars, or in this case, diamonds, to how effective an AEB system is. So for example, 5 diamonds basically means that the system can drive, can prevent an accident up to a speed of 70 miles per hour. And also it has dynamic, driving capability where it can intervene and then basically do this collision avoidance by maneuvering both the front and the longitudinally and laterally away from the accident and the risk scenario. Right. So for example, they come up with labels on the right-hand side, which shows you like, okay, this particular vehicle has a 2.4 star rating for automatic emergency braking. That means that up to a max speed of 40 miles per hour, AEB will work fine, and it also has some moderate amounts of false positives and false negatives. So then you be the judge, how much are you willing to pay for the system? How much do you think the system could be trusted? So those are like deeper questions to be asked about these systems that are making decisions on behalf of the humans, like that, right? So later in this course, you will learn object detection and tracking for overtaking in a head-to-head race with other cars, but you will be building on top of your AEB system. So it'll always be on, but you're still going to try to do aggressive maneuvers in and around vehicles. And then you will also learn after that reinforcement learning based approaches for building your safety car. So then now you will let the machine, explore the area and decide itself how to detect critical obstacles and execute evasion maneuvers on its own, right? So as it is going to go headlong into a wall, it'll actually stop or it'll avoid the wall because it has been trained to do so. But first we will learn it on our own. So as we start to race against cars later in the semester, you learn, how to do overtaking, perhaps even with some drifting. And in order to satisfy this safely, you will build on these AEB basics and add object prediction for possible trajectories the opponent could take, and using the vehicle's dynamic model with tire models, cornering stiffness, and also some way of estimating the opponent behavior and the potential for collision. You will then design planning algorithms that will need to decide what is the lowest cost trajectory that can avoid a crash, but successfully execute an overtake maneuver. So we are trying to balance, safety and performance later in the semester. So that your control algorithm eventually will have to need to tightly follow this trajectory while driving at the limits. So this is a great way to learn why AEB and its extensions can save lives and of course win a race, right? So by learning to tune your vehicle's planning control decision system to minimize false positives and false negatives, you develop useful skills as an autonomous engineer. And here you see this happening both, between, two cars racing head to head, so they don't crash into each other, but still are very aggressive. So now let's start getting more real with our systems. But first, we understand what is the variety of sensors that are available to and often used in autonomous vehicles. And for you and me as humans, we have 2 eyes, which allow us to detect, classify, track multiple objects. So why do we need so many different sensors on an AV, right? So why can't we just use a single camera or a radar? So the nice part is we get to understand what these sensors do and how they do them. And then we see how we can put a system together with some of these sensors. So for situation awareness, a vehicle needs a 360-degree understanding of its surroundings with multiple sensing modalities, right? So long-range LIDAR to provide a 200-meter plus look ahead for the vehicle to plan its trajectory. Radars capture the distance and the speed of obstacles for collision avoidance. And then cameras classify and track objects for better context, right? So, and then ultrasound is used for blind spot warnings and parking assistance. So the RGB depth camera is the first sensor that we look at. And this is an example is like the Intel Realsense D435 is cheap and versatile for stereo vision, right? So it basically provides a point cloud with distance estimates, works outdoors, and also has an IMU integrated for the detection of the movement of the camera. So the working principle is an active infrared stereo and normal computer vision camera for object detection here. So we can basically get color depth images. The disadvantage here is that it has a limited range of about 6 meters effectively. And then it can get noisy in low light conditions and requires building a custom Linux kernel. That said, overall, it's a great sensor. It's a good setup for robotic applications like the F1TENTH. And we have several of them for you to use. And the nice part is we also have a guide that's prepared by former students that took the course on how to easily install it and get it running in a few minutes. The next sensor we'll look at is the Z and also the Z2 cameras made by the Z startup company. And this offers an excellent stereo vision solution. Using 2 cameras, it calculates the depth using stereo vision, stereo multi-view geometry. And all this is done inside the camera. The system has good computational power on board inside of the camera, which gives us 2K resolution at 30 FPS, and then a 1080p resolution at 60 FPS, which is really good for our kind of robotics application. It also has a good range. The advertised range is about 20 meters, but effectively we've seen about 12 meters of range, and then the noise starts to increase. And it has good outdoor performance and good scalability because there are many Python-based examples in the SDK. And all the sensors I'll talk about today, they all have ROS drivers and interfaces, and they easily plug in and can be installed in the system with no hangups. So this system also includes a calibrated IMU to detect camera movement. The disadvantage is that they have low texture surfaces, given the IR cloud that it has. In this case, it does not have an IR cloud, unlike the Realsense. So the other sort of limitation is that the baseline width between the 2 cameras, that limits the range, the depth range. And then the processing is a good amount of processing that is now offloaded onto the computer that is now getting this very high resolution, high FPS system data. And so you need to have a computer that is that can run CUDA. And the upside is that the NVIDIA Jetson that we use on the car can run this sensor very effectively, and we have many of these sensors handy too. So then we look at monocular cameras. That's the very basic building block of computer vision. And so with classic computer vision, you can capture the vanishing point down a corridor, you can detect lane markers, and so on. The nice part is that we can also detect depth with monocular cameras nowadays using machine learning approaches such as monodepth, right? So with supervised learning on the LiDAR and the monocular camera data, we can capture relatively good depth estimates, making this a cheap and powerful depth sensor. The best case error, unfortunately, in this is about 11%. So for an object that's 80 meters away, there's an error of about plus minus 4 meters. And so this is good for many applications such as overtaking on an F1TENTH, but it's not sufficient for safety critical real world driving like that, right? So on the F1TENTH, if the cars are kind of meant to crash because that's what we experiment with. So in the bottom right, you can see monodepth in action, and you can see it's actually really impressive. In the past 3-4 years, actually, monocular depth perception has advanced significantly. The third sensor we'll have a look at today is the radar sensor. Radar is very old, and it's used extensively in the automotive industry. Here we have a continental radar series, which include a long-range detection for AB and a short-range detection for parking and pedestrian identification. Radar works by emitting radio frequency or RF energy and measures the echo afterwards. Using the Doppler shift, this principle allows for detection of moving objects and where we can capture the velocity of another object. One disadvantage of radars is that they have poor spatial resolution and a narrow field of view. They cannot classify objects, but radars are robust across a range of environmental conditions. They are relatively insensitive to temperature changes and have longer ranges than comparably priced LiDARs. Most AEB systems on the market are radar-based. The fourth sensor here is the ultrasonic proximity sensor. It works by measuring the time of flight of high frequency ultrasonic sound pulses. They offer good accuracy, are super cheap, and have a small size. They're used for parking applications and for blind spot detection. These systems work for close ranges around under 5 meters and have a narrow field of view. So they may not assist with autonomous navigation per se, but they're very good for local situational awareness. In the bottom right, you can see an example of parallel parking using an automated parking application using the F1TENTH. And this is an example of how a radar could be used to identify near objects. The LIDAR, depending on whom you ask, stands for light radar or light detection and ranging. A LIDAR provides depth or distance information, how far from the car are the objects in the scene. This is one of the most important sensors in the field of autonomous driving. Traditional LIDAR systems are electromechanical systems, which basically are a spinning laser system. They emit photons and which reflect off objects, and the time when they reach the collector is used to provide a very accurate distance estimate. The moving parts restrict the size and also make it a pretty expensive sensor. We use a Hokuyu Planar, that's a 2D 10LX LiDAR, and the model number is named 10LX, which basically costs as much as all the other F1TENTH components put together. But it is a very versatile and useful LiDAR. One disadvantage is that it only works in, when we have a flat surface. If there is a slight ground tilt, that makes it difficult to localize and navigate the vehicle as it is now scanning something above the ground, above the surface. The benefit of using the LiDAR is that it is compatible with the ROS and it has simple data structure to process. It also has very high update rates and very low processing requirements as it is just a 2D LiDAR. So now moving on to 3D LiDARs, which are standard in many of the autonomous vehicles out there today. The 3D LiDAR is basically like a 2D LiDAR, but it's stacked up, and it could have anywhere from 8 to 128 layers that are detecting objects in the Z direction too. 3D LiDARs have become very good in the recent times with over 200-meter ranges, a sub 10 millimeter accuracies, and a 360-degree field of view. Here on the right side, you can see the Ouster LiDAR, which is very good at detecting trees, people, vehicles, and can directly be used for object classification. On the bottom right, what you see is a point pillars, which is a paper and an approach for fast encoders for object detection from just LiDAR point clouds. So it's able to do effective object detection without the need of a camera and directly from these high resolution LiDARs. In fact, these 3D LiDARs are also used to build high definition maps that most first generation autonomous vehicles are using in development. The disadvantage is, once again, that they're very expensive and they have relatively low reliability compared to radars as they have moving parts. So processing the point cloud is also very compute intensive, and you get tons of points of data that you have to process in real time. So most LiDARs have ROS drivers and also GPU point cloud processing in CUDA that makes it effective to do in real time. So finally, there are solid state LiDARs such as the Velodyne's VelArray on the right side, that don't have moving parts. And this will eventually become the more economical LiDAR option, as it will be cheaper to produce and is also not sensitive to vibrations and can be made fairly compact. To achieve a scan, the solid state LiDAR uses a phased array where the phase angle is modulated across several transmitters to create a directional broadcast. And so the phase arrays can control the size, the focus, and the direction of the broadcast to scan the target region precisely without any moving parts. Right? So solid state optical emitters are arranged in layers to achieve an optical phased array, and groups of these optical emitters then send out bursts of photons in specific patterns and phases to create a directional emission. The focus and size can be adjusted to have greater precision in certain regions requiring more attention and coarser resolution in peripheral regions or regions with less movement. So this is very good for like anticipatory sensing and more adaptive and agile sensing applications too. So in the bottom right, what you see over here is an example of the well array being used in a parking lot to identify empty parking spots, right? And this is a very good application where it is suitable for. So solid state LiDARs are basically new entrants in the market, and there's a lot of startups pushing this frontier, and there'll be a lot of exciting new products in the coming years. So now let's look at what you can do with working with the laser scan data on the F1TENTH car, right? So LiDAR that we have is typically placed on the top of the car to have an unobstructed view of the scene. We use the Hokuyu 10LX, which basically has a range of 10 meters and can detect objects up to 10 meters robustly. And the basic idea behind a LiDAR's operation is simple enough. The LiDAR shoots a laser beam at an object and measures the amount of time for the beam to be reflected back. Half that time multiplied by the speed of light gives the distance to the obstacle. That's the basic idea. Of course, many factors complicate this picture, such as temperature variations, surface reflectivity, or angle of incidence of the laser on the obstacle, or sometimes even the color of the obstacle, or how much fog or rain is there in the atmosphere. But for our applications that we are driving indoors, it's a very reliable, distance measurement sensor. So the LiDAR does not shoot just a single laser beam, right? That would be not much use. So the LiDAR we use basically scans the environment at a rate of 40 Hertz, meaning that it sends out lasers once every 25 milliseconds. Every scan produces 1,080 rays separated by 0.25 degrees. That's the angular resolution, right? So if you add it up, it means that it covers 270 degrees horizontal field of view 40 times a second. So the ROS message structure for LiDAR is pretty straightforward, as you can see on the right-hand side. All you have to do is subscribe to the LiDAR topic. You can choose the min and max angles. So for example, if you want to focus on a narrower field of view to reduce the point cloud processing, you can adjust the min and max angles over here. So the most important field, in this ROS API for the LiDAR is the float 32 ranges. This is the array of distances to the obstacles in the scene. So element I of ranges is the distance of the object along step I. Right? Recall that step I is I plus the first laser beam produced by the LiDAR. And there are 1,080 steps for the 10LX LiDAR we're using. So for example, let me set up a simple scene first, right? So we have a top view on the left of a room with the LiDAR in the bottom corner. And a person starts by walking in front of the LiDAR facing the whiteboard, right? So the LiDAR sees the world as points. And as you can see, the red points all around the room over here, right? So occlusions can occur when one object hides the other object behind it, right? So, and basically every point corresponds to a laser beam bouncing off the object, obviously. So as in this case, the whiteboard is, hidden by the person. So moving group of dots that you see, as I just replay this video again, is the person backing away from the LiDAR, and then they're moving closer, and then to the right of the LiDAR, and then dropping out of the field of view. So this LiDAR is a very effective sensor for our, indoor applications. If you listen to the LiDAR ROS topic, you will see this array being printed out in the terminal. Each array comes from one LiDAR scan, one time instance. And measurements outside of this min-max range, they are to be discarded and not reliable. You see also some infinities over here. That just means that the object's range or the distance of the object is beyond 10 meters, and the LiDAR cannot reliably detect any object along that path. So you could, and later on when we start to look at reactive methods of mapless navigation, we'll see algorithms such as follow the gap that essentially use this information to do very agile collision avoidance and obstacle avoidance, and navigate, quite dexterously through a corridor. So here we see the LiDAR now driving on board the car, and and we can see as it's navigating through the hallways, walls within the LiDAR range are detected. So now as the car comes to the end of the corridor, notice the T-junction, and you'll get to see an outline of that floor over here, right? So, and you will be soon driving the car autonomously in this manner in just a couple of lectures forward. So as we're getting to implement now, AEB, we first need to come up with a good measure for safety. And so, for example, we can see that there are, we want to use safety as this indicator function, but we want to sort of understand, what's the extremes of this safety, right? So you can see in this video over here that, safe AEB with moving obstacles. And so this car in front was, has a sudden brake because of the car in front of it braked and was making this crazy move to the exit. But this vehicle, it executed the AEB, stopped, and also did an evasive maneuver successfully. Right? So, but now on the right-hand side, you can see that, this car is driving down the highway in China at about 55 miles per hour. And then on the left, there is a stopped street cleaner. And no AEB is triggered for this stationary object in the driving path. And this results in a fatal accident of a 23-year-old. And that shows like a failed case where the AEB clearly could not detect a stopped obstacle or stationary object. So this takes us to the next level of how do we start to understand safety, right? Defining safety as a binary for safe and unsafe is an oversimplification, right? So so safety needs to be considered across a spectrum of scenarios, environments, interactions with other vehicles. On the left, we see an example of Comma AI's open pilot system, which uses a monocular camera for end-to-end autonomous driving. Many consider this to be quite a risky approach. And so this video is like an example of 100 highway miles with no AEB encounters, no disengagements. So I would call this as good anecdotal evidence that the system functions. Now, how safe is the system? You're not going to be able to say that in 100 miles on a straight highway, right? But at the same time, this gives us an idea of what is the kind of performance that we want from our automated driving system. So when AEB is needed, it must perform this maneuver safely in time and in space, right? Because it is overriding the driver's input. So now we need to understand how do we capture this time and space in a very simple form that we can use in our code then. So, so this combination of we could just use the Euclidean distance, right? So it's easy to compute. We have sensors that can measure the distance, and it can be accurately captured also, right? So here we see examples of how this vehicle is capturing any object that is in front of it and stopping in time by applying AEB. But Euclidean distance does not capture the relative change in distance or the relative velocity of the other objects. So here, if you're standing at like a T-junction and vehicles are passing by you, their relative distance may be small, but that doesn't mean that you execute AEB in this case, right? So one way to reason about this is to capture both the relative distance and also the rate of change of that distance, right? So we use this approach or this concept called time to collision. And TTC is defined as the time it would take for this ego vehicle, that means our vehicle, and an object to intercept or to crash into one another, given that they each maintain their current heading and velocity. Right? So, and then based on this TTC threshold that we will define, we can then decide what kind of brake pressure or brake reaction. Should we just have a notification? Should we have a light, moderate, or a full braking force to get the vehicle to safely come to a stop? Right? So TTC is defined as the time it would take for the ego vehicle and this object to crash into each other. And so essentially we look at this as a ratio of the range or the distance between the vehicle and the object divided by the time derivative of the range or the rate at which this gap is becoming smaller, right? So because the gap is becoming smaller, it's a negative value. So that's why we have the negative sign to make it positive over here. And so this time derivative of the range between the vehicle and the object is also called the range rate. And essentially, we also have this positive operator on the brackets over here to basically say that if the vehicles are separating, that means they are moving apart, then we basically just treat it as TTC is going to infinity. And but if the vehicles are coming closer together, that's when we have a positive time to collision. And that's when our system starts to become more active. But we ignore any of the vehicles that are basically, where the relative distance is increasing, right? And it's increasing at a faster rate also. So how do we compute this range rate? The range rate is basically the time derivative of this distance, which is simply computed by projecting the relative velocity of the vehicle onto the vector between the vehicle and the object poses, right? So we have Vx, which is the forward speed of the vehicle's reference frame. And this is simplified because we're not dealing with moving objects in the safety lab. We're just going to have stationary objects to begin with. And then we multiply that by the cosine of the beam's angle. This is your LIDAR beam's angle over here to get project that vector onto the path of the vehicles in the vehicle's direction. So now with this planar LIDAR, given that we have a ROS interface and we are able to capture control both its field of view and capture the distance estimates using our planar LIDAR, we can now compute this this TTC by having an acceptable threshold when we should apply the brakes, right? As I mentioned before, if this TTC is, say, below one of these three thresholds, then we can apply, just have a notification, have a light, moderate, or a heavy full braking pressure and have TTC actually be even further discretized rather than just, a binary like that, right? So for example, when we start to look at inputs into, say, any kind of learning system, a lot of interview questions focus on things like how would you build the system, right? So one sample interview question for you is describe a feature which captures the relative pose of all vehicles in the vicinity of the car, right? So what feature would that be in terms of, like, assuming you have a LiDAR, right? And then what if that feature is used as an input to a neural network and the number of vehicles changes, right? So initially you could have a certain set of numbers and now there are, more vehicles or less vehicles, right? So will this be a problem? Why or why not? So let's see what's coming up next, right? Now that you're going to start to implement AEB, so you'll actually implement it you'll implement TTC based on the safety node in the simulator first. And essentially you'll have keyboard control and try to crash the vehicle into the corridors, as you can see on the left video over here. And AEB should essentially engage whenever you're about to crash, right? And then you'll tune the AEB to reduce the false positives and false negatives and basically have a pretty rough manual driving through this corridor map over here and demonstrate that, while you could have had many crash incidences, you have a crash-free lap with several AEB activations, right? And that basically is showing AEB in action with a terrible manual driver, right? But that's the way we start, right? So now let's see, and this is what you will, once you are able to do something in the simulator, then we give you the car and then you can actually run this lab in the car and basically show us how you don't crash into all these boxes and into the corridor. So in the next upcoming lectures, we will study pose transformations, so rigid body coordinate systems for rigid bodies and transformations for them. And that's a good way for us to capture, an integrated view from multiple sensors and also to be able to help us localize our vehicle within a map, which will eventually help us then to plan within that map and then to race within that map using map-based techniques. But before we go all the way there, we want to just capture the basics of post transformations. And we also will study mapless autonomous navigation, right? Just using the LiDAR without any map, how can you do very agile obstacle avoidance and follow the wall? And essentially that will be part of your first race. You'll also get to build the car over here and be able to tune it, right? So that's very exciting stuff coming up. And we're looking forward to the next lecture then.